This is the lecture on body composition for the level 1 course. The goals of body composition analysis are to assess the current state, to compare or classify versus a reference and determine the status. This reference can be a normal population or a specific athletic population. Could be children's data. Secondly, to help and design nutrition and exercise interventions to modify this body composition. For example, to assess how much body weight needs to be lost or gained, muscle mass gain or fat loss. How long it will take to achieve this goal. For instance, the average 1 pound per week fat loss goal. Of course, there's a whole variation according to that. See how we, month by month or week by week, how close we are to staying on the right track to achieve that goal. So those are the main objectives. Now, there are many types of body composition analysis. The one we're going to talk about now is mainly this one, the chemical molecular level, that divides the body into two components, fat or lipid, chemically defined, and fat-free mass, which is composed mostly of protein, water, and other chemicals. With this system that began with underwater weighing in the 1940s, there are some classification standards. For example, it is assumed that essential fat is between 2 and 5% in males and 10 to 13% in females. Now, this is somewhat controversial. Some people may have more, some people may have less, but it's like a ballpark figure. Then athletes would have between 5 and 13% in males, 14 or 13 to 20% in females. Then you have fitness categories, you have average population standards for body fat. And then the obese is classified as having more than 25% body fat in males, more than 32% in females with this method. This is another chart that stratifies the categories of very lean, ideal, average, or above average, according not only to gender, but also to age group, okay? So if somebody is to have, for example, 22% body fat, okay, 22.8% body fat might be okay for someone that's 56 years old, but it might be far too high for somebody that's 18 to 20 years old, okay? That would put them over there. So as we age, we tend to accumulate more body fat, especially in the abdominal visceral adipose tissue region. Now, we have over 100 equations to estimate body fat. There are some which are for children, like the Slaughter and Lohmann equation from 1988. There are some which are for adults, depending on ethnic background, gender, whether using skin folds or bioelectrical impedance, and there's some for senior citizens. So what's the idea? The idea is to choose one equation that fits or that was developed with a sample of the population that's similar to the one that you're measuring. For example, if I'm measuring athletes, I want an equation that was developed in athletes, like the Withers 1987 equation, the Jackson and Pollock equations, some of the McCardle and Catch equations, or Lohmann equations. If I am measuring average population, I might use Durning and Wormsley 1974 equation. to give you an idea. Now, I have seen papers published on athletes, and their body fat was reported with a Dunning and Walmsley equation, which gives you slightly higher results. So basically what you have to do is to see what equation did the authors use to develop the database, the reference database that you are comparing yours against. So for example, I did my part of my thesis, my nutrition thesis on the body composition of female field hockey athletes. And the reference data of the Dutch national team, which are some of the best in the world, was reported with a Dunning and Walmsley equation, which shouldn't be the case because that's an equation for non-athletes. However, if I wanted to compare my data of my players against their reference ideal data, I had to use the same equation. That's just to give you an idea. So basically use one equation. If you're following somebody longitudinally across time, you want to stay with that equation and see how much they change from, say, month to month. Here is an example. I have an Excel spreadsheet with 8 different body fat equations. Hugh has, Withers, Wilmore, Thorland, Sloan, Catch and McCardle, Forsyth and Sinning, Dunning Walmsley. And I took the skinfuls of just one person, plug them into these different equations, and I can get from 10% body fat all the way to almost 20% body fat. So there's a 10% variation according to which equation you are using. So this is confusing, and we have to be very specific about, if we talk about body fat or read about body fat in a book, it has to say how that equation was developed, or which equation they're using, to report the data. For example, the Withers, which are for athletes, can give you 14% body fat, and the Dunning and Walmsley can give you 19% body fat. So we must keep that in mind. Now, these are average percent body fat for athletes, supposedly done with underwater weighing. So for example, we have basketball in males, 6 to 12% is the average of the elite athletes, and females 20 to 27%. If we have swimmers, 9 to 12, 14 to 24. So here we have different values or estimations that have been reported in the literature or in the bibliography, scientific bibliography, on elite athletes. Now, these are some of the body fat estimation charts, so you can eyeball and get an idea of what corresponds to, for example, 5% body fat, 10% body fat, 20% body fat. So in males at 10% body fat, your abs should be showing, okay? 3% body fat, that's really low. You're either genetically there or you've taken some performance enhancing drugs to achieve that. Same as in females, okay? Between 15 and 20%, that's an athletic body type, similar to 5 to 10% in males, okay? And at 40 to 30%, we have too much body fat. And in females, between, I would say above 32 to 35% on there's too much body fat. So this is just an estimation, just to give you an idea, if you're not familiar with it. Okay, so in sports, let's go through a few examples. In bodybuilding, fitness, you try and achieve your minimal levels. Males between 5 and 8%, although in this picture, this guy looks like he has 2% or 3%. And in this picture, we have a female that's about 10% to 12% body fat. In road cycling, you need very low standards. Again, okay, very low body fat percentages, especially in the males. In CrossFit, okay, you have about 8% body fat, not the lowest level. This is not a bodybuilding competition. You have to eat. You don't have to diet so much that you lose body strength. And then you have some additional data here in body proportions, like a short humerus arm, a long torso, a short femur for squatting and for pressing movements. Short humerus helps. This is the average height, which is about 5'10" and a half in males. The average weight, which would be about 196, 198 pounds. Okay, just to give you an idea. And wingspan, okay, or arm span as we call it, is plus minus 3 inches related to height. In females, again, body fat is quite low, 15%, but not the lowest. You have a lot of muscle. Females are about 1.65 meters. That's about, well, let me make that quick conversion for you. That's 165 divided 2.54. That's 65 inches roughly. Okay, so that's about 5'5", and 66 kilos divided by 2.2, multiplied by 2.21. That's about 145 pounds. So a lot of muscle. Okay, and then again, same with the wingspan. Long torso, short upper arm, short upper leg, in order for pressing and squatting movements and clean and jerks, gymnastics. Now, the sum of skin folds just by itself, you can measure these 6 skin folds, one from each body part: the triceps in the upper arm, subscapular in the back of the trunk, supraspinale more towards the side, abdominal more towards the center. So we have 3 skin folds from the trunk. You have the front thigh skin fold and the calf skin fold. So you have like 1 skin fold from every body part. If you just add them in millimeters, you can do that quickly, and you have a very good quick estimation of body fat, which doesn't include the error of inputting or plugging these numbers into a body fat equation that will give you different results and will confuse you. So personally, I really like the sum of 6 skin folds, also called the Olympic 6, because Lindsay Carter first used it at the Mexico 1968 Olympics on 800 athletes measured over there. Then at the Montreal 76 Olympics, they also used the sum of 6 skin folds. And in many world championships and on many athletes, we report the sum of 6 skin fold, which is a quick and easy method. You just have to get used to the values. For example, the ArgoRef sample is a sample of young 20 to 30-year-old dietitians and physical education teachers that are in good shape. They're not elite athletes, but they're not sedentary, they're not obese. And these are the percentiles for, say, females and for males. And we assume that between percentiles 15 and 85 is the average or the normal. So you can say that for females, average values for fit young females, average values for the sum of 6 is between 70 to 120 millimeters. And for males, we round the figures, say from 50 to 100 millimeters. Usually athletes fall in the lower end, and minimal values for females would be about 40 millimeters, and for males about 30 millimeters, just to give you a quick idea of where we stand. Average values, 90 to 100 in females, 65 to 70 millimeters in males. So this is a very quick, simple method. You just measure 6 skin folds, you input the data into a calculator, and you get a result, and you become familiarized with it. This was good when you don't have too much time to measure athletes. Like, for example, it was my case in elite soccer. I had a couple of minutes to measure athletes, so I would weigh them. get their skin folds added up, and they knew they had to be at 50 millimeters or below in male soccer, or 70 to 75 millimeters or below in female team sports. So these are athletes for sum of 6 for male athletes from Carter, marathon runners, long distance runners. Look at them, very low values. Olympic walking, speed walking also, middle distance values, sprinters, they're all below 40 millimeters, okay? Then you have jumpers around 40 millimeter mark. These are throwers at the 96 millimeter mark, so they can have much more body fat. These are basketball players, a team sport, between 50 and 75, depending. Cyclists at 44, this includes track cyclists that have more than the road cyclists that usually have less. Soccer around 50. Weight category combat sports, depends on the weight category, they can be really low. Swimmers around 50 to 45, elite swimmers, kayakers, rowers. This is Olympic shooting at 107, triathletes at 49, volleyball at 49. So that's just to give you an idea of male athletes, okay? These are female athletes going as low as in the mid 40s, in the marathon, long distance, 57 middle distance, 56 sprinters, around 50 to 60 in jumping events, and fencing, 72, artistic and rhythmic gymnastics around the low 40s, field hockey team sports, 70 to 78, swimmers, 83, rowers, kayakers in the 70s, okay, Olympic shooting, 115, triathlon, female triathlon, around 60 millimeters. So that's just to give you a rough estimate of where elite athletes position themselves on these sum of 6 skin fold reference. Now, we can use body composition to estimate the ideal body weight. And the equation is this: your current pounds or kilograms of fat-free mass or lean body mass divided by your ideal percent fat-free mass. So how do you calculate your current fat-free mass? That's easy. It's just your weight minus how much fat you have in pounds or kilograms. And how do you determine your ideal fat-free mass, percent fat-free mass? That's 100% minus your ideal percent body fat. Okay, so let's run through an example. Here's a soccer player. He is 5'9", weighs 154 pounds. His body fat is at 15%, and he wants to go down to 10%. So what is his ideal body weight, and how much fat does he have to lose? We're assuming that he preserves his fat-free mass because his diet is good, he has enough protein, he continues to train, and his calorie deficit is not too big. So the answer is, he weighs 70 kilograms, 154 pounds, times 15%. He's got 23 pounds of fat. Okay, so what about his fat-free mass? That's easy. He weighs 154. We take away 23 pounds of fat. He has 131 pounds of fat-free mass. What is his ideal percent body fat? So it's 100 minus 10. Where did that 10 come from? Because that's the ideal body fat. So 90% would be the ideal fat-free mass. Easy enough. So his ideal weight would be 131 pounds divided by 0.90, which is the same as 90%. So he would weigh 146 pounds. He's now weighing He's now weighing 154, so he has to lose about 8 pounds. Okay, that's the way we work the math, the simple math on finding ideal body weight. Now, this is an interesting calculation that has been getting more and more popular, which is called the fat-free mass index, the FMI. Basically, it's your fat-free mass divided by height squared. So, and this is done in kilograms and meters squared. So this would be the same as the body mass index, but instead of dividing the total weight by height, you're just dividing the fat-free mass by height squared. This is to get an index of how muscular or how lean someone is independently of height. Because obviously taller people have more fat-free mass than shorter people. But what about if they both had the same height, or if we standardize height to height square? That's why we do the same thing with body mass index. This is what we get. Now, which are the normal values? Okay, this is a study published on 3,000 men and 2,600 women, stratified by age and gender, males in gray, women in white. So here's the fat-free mass index. So for example, males, 19.1 kilograms per square meter is the average, and in female, it's 15.9. And here's the standard deviation. Of course, there are differences within age groups, but this can be a good standard. So if we add or subtract one standard deviation from the average, from 19.1, we get that the range for males is 17.7 to 20.5. And for females, the average is between 14.6 and 17.2 kilograms per square meter. So if they fall within these ranges, we can say, okay, their lean body mass is normal or average. So going back to our example of a soccer player, his fat-free mass was, he had 23 pounds of fat, as we know, and he had 131 pounds of lean body mass. So if we divide that by his height squared, it would be 59 kilos. His lean body mass in kilograms divided by 1.7 squared his height in square meters. So his fat-free mass would be 20.6. That's above the male average of 19.1, if you recall from the previous slide. So he's at the upper level in his lean body mass. Now, would that put him in the upper level of soccer players? Or is that average for soccer players? Okay, we would have to calculate what's the fat-free mass index of elite soccer players in order to answer that question. So there's a lot of reference data on athletes on fat-free mass index that we don't have, but we have to build those databases. Now, this is popular in social media. They say that the average is between 18 and 20. If you lift weights, if you work out, you can go up to 22 or 23. That's excellent. If you're genetically excellent, you're up to 24. They say the upper natural limit is 25. And that they say that if you're 26 or above, you're probably using steroids. Now, I found this not to be true, because there's people with large bone structures that can be at 27 or 28, and they're completely natural. They're not taking any performance-enhancing drugs. So this classification that you see in social networks, I wouldn't really trust it. Okay, you can't accuse someone of being on PEDs just because they're above 25 or 26 in the fat-free mass index. Okay. Now, regarding bioelectrical impedance machines, you have two types. You have monofrequencies, like these handheld devices, or you have these weighing scales. These usually cost around $50, and these are called monofrequencies. And then you have multi-frequency devices that are $3,000 to $5,000. Is there a difference? Yeah, there is. These guys really are not measuring. Basically, they have a small software inside that estimate your most probable percent body fat based on the data you put into this computer, your age, your gender, your height, your weight, and your level of physical activity. These devices are much more accurate in predicting body fat and lean body mass. So if you can do your own test, you can calculate your own percent body fat, entering the required data, gender, age, weight, height, physical activity level. Then you can erase your result, see your result, record it. Then you can erase the results, and you can repeat the procedure, plugging in different data, okay? For example, a different height, a different age, a different weight if it's a handheld device, a different gender if you want, and you'll get a completely different result. Why is that? Because this is not really measuring. It's estimating your percent body fat based on that data that you input. So the monofrequency machines, I wouldn't trust them. The multi-frequency ones, yes. Now, there are equations to assess muscle mass. These are some of the most popular ones. The Lee et al. Equation from 2000. It's a multiple regression equation based on 244 non-athletic adults. So some of the exclusion criteria is to be training or to be an athlete. So a lot of people use this equation for athletes. I don't know if I would do that. The Allen-Martin equation is based on 6 age male cadavers. Again, this equation overestimates the body composition in athletes, and this one may underestimate it. Then you have the 5-way fractionation, Kerr and Ross anatomical fractionation equations, and they can be good for any sample, especially athletes, but you need measures that are not in level 1. You need it for, you can only use it at level 2. Once you know how to make an additional 8 measures that you learn at level 2, unfortunately. But still, you can use the Martin or the Lee equations and compare them against reference data. For example, the Allen-Martin 1990 muscle mass equation uses 3 girths: forearm, which you have to learn from level 1, it's at the maximal girth below the olecranon, mid-thigh and calf, which you know, and then a couple of skinfolds, thigh and calf, and height. And these are values in kilograms, say, for bodybuilders, for basketball players, for power athletes, for gymnasts, for long sprint athletes, non-athletes, and distance runners, which actually have less muscle mass than even sedentary people than non-athletes. So you can use this equation and compare it to different databases or before and after to see the evolution of muscle mass. Then you can estimate the skeletal mass with this Allen-Martin equation, again developed from Carver data. Basically, you have to measure 4 bone breadths: the humerus, the femur, the wrist that you learn in level 1, and you have to add the ankle breadth, which we can cover in the course, which is usually your bimalleoli, between your 2 malleoli in the ankle, and the caliper is put at a slight slant because of the way the malleoli are in the ankle. With those 2 equations, the muscle mass and the skeletal mass, you can estimate a very interesting index called the muscle to bone ratio, which is basically your muscle mass divided by your skeletal mass. Now, you want to keep some coherence between equations, so I would suggest using both Allen-Martin's equations, not mixing equations. And here are average values for a normal population using the Martin equations. So for example, in females, mean values are 25 kilograms of muscle and 6.8 kilograms of skeleton. And the mean muscle to bone ratio is 3.8, with an upper cutoff at 4.5 and a lower cutoff at 3.2. For males, 42 kilograms of muscle, 9 kilograms of bone, 4.5 would be the average muscle to bone ratio, MBR. 4.0 would be the low end cutoff, and 5.1 the upper end cutoff. So if you know someone has a 10 kilogram skeleton and you want to know how much muscle they can put on, you multiply those 10 kilograms by 5.1, that's 51 kilograms of muscle. And if they have, for example, 42 kilograms of muscle, that means they can put on 9 extra kilograms of muscle. So that's an estimation. Then you have different online calculators. There are many. Here's calculator.net. This is a body fat calculator when people are not using skin folds, or they cannot use skin folds. So you can choose your gender, you can use US units or other units, and you just input your age, your weight, your height, and 3 girths. Your neck, your waist. Neck would be above the Adam's apple. Your waist measure, this will be not the Isaac waist measure, but the widest measure at the level of the iliac crest, or your umbilical button, and your widest hip measure. Then you press calculate, okay, and you have these reference body fat, and it will estimate where you are. For example, with these figures, it'll indicate where your body fat is and whether you're average, fitness, or obese, or whatever. So that's another tool that you can use online. Thank you very much. Hope you enjoy this. Hope this was helpful. And if you have any questions, of course, you let me know.